scientist is even asking for, especially when they give you multiple values in it. So another one that we were working on was density. So we said that density is defined as the mass of a sample divided by the volume. So the more mass something has, the more dense it will feel. And so I think I showed you the little lead piece of the little lead sheet. Well, I got kind of like, I think it's about the same thickness of aluminum. So I took multiple layers of aluminum foil and sort of folded them over and over and over until they felt like they were about the same thickness. But when you hold on to these two, this is the lead piece and this is the aluminum. The aluminum's a little bit bigger, but they're pretty close in size. But when you hold them both, you can definitely feel a difference in one compared to the other. So that lead has a lot more substance to it. So when you just kind of hold and compare the masses of the two, even though they're about the same volume, that lead has a much more dense nature, a much more dense feel. It feels heavier relative to its size. So density is a characteristic of substances. And if you know density, mass, volume, if you know two of the three, you can calculate or work out the third just by rearranging the formula. So this one says a tablet of Tylenol weighs 0.678 grams and has a volume of 0.17 milliliters. So I want density in grams per mil. So in this one, I don't have to rearrange the formula. I can use the formula as is because I want to know what the density is. So I take the mass. Which one's the mass? So this is the mass. And I'm going to divide it by the volume. So those are my known values, and that's going to allow me to solve for density. So when you do the math, did you get all of this? Okay, so this would be grams per mil. So I had grams divided by mil, so my units are what I want. But can I keep all of those? No. Okay, so since these are measured values, 0.678 has how many significant figures? 3. So this one has 3 significant figures. 0.17 has 2. So that means that I'm going to have to round to 2 significant figures. When you multiply and divide, round to the smallest number of significant figures in the measured volumes. So that means this 3 and this 9, those are the first 2 significant figures in my number. That means I got to do something with the rest of it. So the next one's an 8. So what will that do? It'll round up. So it'll round up to 4.0. So I keep the 0.0 because that keeps 2 significant figures. 0's after a decimal place. 0 is at the end if there's a decimal place, are considered measured values, so that'll keep the right number of significant figures in it. So we talked about specific gravity, looking at like more concentrated and less concentrated solutes. Talked about temperature. These are really the 4 sort of comparisons in Celsius and Fahrenheit that you need to know. So you should know boiling point of water is 212 in Fahrenheit, that it's 32 is the freezing point of water in Fahrenheit. Body temperature is 98.6 in Fahrenheit. Room temperature 75. okay? But then their corresponding Celsius values, boiling point, freezing point of water is where they got the 0 and 100 scale for Celsius. So that one's pretty easy. Remembering body temperature at 37, and then room temperature is about 25, 75 Fahrenheit, 25 in Celsius. But those are really the only ones. You would need to actually use a formula to be able to convert from Celsius to Fahrenheit or Fahrenheit to Celsius, because they have different zeros. But just knowing those 4 basic ones are fine. And then the last thing is we were talking about Kelvin. You know what Kelvin means in comparison. We'll talk about things in terms of Kelvin when we talk about gases. So Kelvin is based on a scale of what they call absolute zero. Absolute zero is the temperature at which molecules stop vibrating. So it is the coldest that any substances can get, because remember that temperature is a measure of the vibrational activity of molecules. So when they stop vibrating, that would actually be what they call 0. So that is the coldest possible. And they have actually chilled molecules down to within a degree or 2 of absolute 0. It's minus 273 degrees Celsius though. This is super cold. So environmental temperatures, you don't find this, but they've actually been able to use like super refrigerants in order to be able to chill it down to this. So we talked about, so temperature is vibrational activity, while energy is that ability to do work. Potential versus kinetic. So potential energy means like this is energy that could do work, but it's not doing work right now. So if the food is uneaten, if the light switch is off, if you're not moving, that's all potential energy. You could move. The lights could be on. When they're on, it's considered kinetic. So that's active energy or energy doing work. The joule is the metric form. But when we talk about food energy, we talk about calories. So nutritional calories, this is the amount of energy contained within food molecules. So we will talk again about the calories. In fact, we're going to burn nuts in lab. So if you're in the lab, we'll burn nuts and then calculate just how much energy is actually given off from the oils in the nut as it burns. So correlate that to like nutritional content and calories contained that you would get when you digest them. And then sort of the last topic I think we quit with was then relating heat, this flow of thermal energy from warmer things to cooler things, and a substance's ability to absorb this energy and then change temperature is all related to specific heat. So specific heat, if you look through like this list, you'll see that water has some of the highest specific heats of any of the substances that are listed. The human body, it says that it has a pretty high specific heat, but that's because it's 2/3 water. So that's the reason why it's as high as it is. But then when you start to look at the metals down at the bottom, like stainless steel, water is 1. Stainless steel is 0.12. Copper is 0.092. So what that means is when these metals are heated, they change temperature rapidly, right? So when you heat a pan, it's going to change temperature much faster than the water that's contained within. So you have to continue to add more and more heat. So it takes longer for that pot to boil, but the pot gets hot faster because metals are going to absorb energy and change temperature much faster because of that specific heat, which is good because you don't want the pot to absorb all the energy. It's actually better that it transfers that energy to whatever food, nutrients, water, whatever you're cooking inside, which is mostly water, and that's going to then increase the amount of energy contained within. So then in the last, and we've really talked about these, states of matter, solids, liquids, and gases. So I brought like some ice and I have some water. So that's if those are pure substances. So characteristics of them. When thinking about the solid, like the solid of ice, the regular, more rigid arrangement of molecules, Liquids, though, molecules can slide around each other. That's how come it can flow. If I had a gas molecules, I'd have to bring like the little hot pot we have. So that, converting that to steam, and then you see the steam consistently coming out as that water gets converted. So we kind of drew like the different, talked about the amount of energy contained within those. But when water is ice and it melts, so as this is sitting, so this initially, I'm already starting to get some. Okay, so as energy is absorbed by the room, because we said that heat is this transfer of energy from warmer to cooler, so the ice is colder, so energy is consistently being absorbed by that ice, and it's causing those molecules to move faster, so they can't stay in that regular rigid arrangement. Now they're starting to move around. So as they're moving around, now they're beginning this melting process. Okay, when this is totally done, it'll just look like this. It'll just look like a cup of water. So the solids will completely dissolve. But is this permanently now a liquid, or can I switch it back? Yeah, I can take this and put it back in the little ice cube trays and stick it back in the freezer, and then I'll have ice again. And what the freezer does is the freezer pulls the energy away, so those molecules move faster. Or sorry, they move slower. They get slower and slower, so they can get closer and closer and like retake that crystalline arrangement. So you can freeze, you can melt, we could boil, and we can condense. All of those things are examples of physical change because the substance is still water. It's still water even though it's ice. It's still water even though it's steam. And so you can convert from one to the other. So in this, I can change it back. So if I take a piece of paper and I cut it into lots of little teeny tiny confetti pieces, is it still all paper? Yeah, it's changed in its appearance, much like the water melting. And I did have to put some energy into the actual cutting of it, but I could like lay them all down so they would all be back together again. So I could rearrange them so they were lined up together. I would have to like glue them or something if I wanted them to stay that way, but that's still considered a physical change. With this, with our little lead sheet, if I took and like rolled it up into a Tootsie Roll, would it still be a little lead sheet? Mm-hmm. Yeah, it's just gonna look different. So physical changes, the substance is still the same, but it may look different. So it might be a liquid, it might be a gas, it might be a solid, but it still inherently is the same thing, and we could switch it back. What about this? So this is the charcoal briquettes. So you pile up your little charcoal briquettes, you throw some water fluid on them just because it makes it more fun, and then you put the match to it, and for the most part, it lights. When it gets done, does it look the same? No. What do you end up with? Ash. Yeah, a little pile of ash. If it burns completely, it's a lot less than what those charcoal briquettes were. Can I take that ash and then change it back into the charcoal briquette? Can I like reform them? That's always a sign that there has been a chemical reaction that's occurred. Okay, compared to physical, where we're melting or we're freezing, the chemical reaction has occurred, the substance looks different afterwards. So I brought 2 strips of metal. It's magnesium metal. I'm gonna hold on to one end. See if I can light it. It's kind of oxidized. There it goes. Hopefully I don't set off a fire alarm. Okay, so did you see that? Yeah. Okay, really bright light given off. You saw this smoke, and now if you look at the two, do they look the same? No. Okay, so the part that burned, if you notice that you see one now has this like whitish ash compared to the unburnt. Okay, so does it physically look different? Yeah. But do you think that I'm going to be able to take this ashy stuff and convert it back after that happens? That's a sign that there's a chemical change. So when you have things like heat release, if you have light release, there's bubbling that goes on. But this is afterwards, so you can see how it's like all kind of ashy looking. So that's a sign that there's been a chemical reaction, a chemical change. This is the one that we burned. That left behind this whitish kind of residue. It's now chemically changed from what its initial one was. Okay, so that's a chemical change. So in fact, their example is with charcoal. I'll give you the chemical reaction that actually occurred there in a minute. So when you have charcoal, so we said that charcoal is black and charcoal is mostly carbon. That was something that we were talking about in lab in that first the safety lab that we did. So carbon is this black solid. And when you light it, you light the charcoal briquette, stays lit, and then you notice it begins to like get smaller and smaller and smaller. So they sort of shrink up over time. That is because of this reaction where carbon is reacting with oxygen and forming carbon dioxide. Well, carbon starts off as this. See the little S? So the capital C is carbon, but in parentheses it has this little s. That means it's a solid. Okay, so S is solid. Whereas oxygen, it's always listed as O2. You'll never see just O by itself. It's always O2 is how oxygen exists. And it's a G, so that is a gas. So as long as there's oxygen surrounding that carbon, it will continue to react. The arrow helps to split. So the arrow, I always say, like, if you have a line down the arrow, line down the arrow is going to help you to split. Everything that is starting material is in front of the arrow. Everything at the end is what you end up with. So the stuff in the front, they call that the reactants. So reactants are always on the left side of the reaction arrow. Products is what you end up with. That's always on the right side. So the arrow sort of splits before and after. Before I have carbon and oxygen, after I have carbon dioxide, I have this CO2. And CO2 is also a gas. So as that charcoal burns, carbon dioxide continues to be released. And that's why it disappears. That's why the black carbon, why your charcoal briquette gets smaller and smaller. It's not really disappearing, it's just forming a gas. And so there's less and less carbon present. And that's why when you're done, all you have is this little bit of residue ash left behind. Other ways that you might see substances listed is they might have an L. So S means, in a little parentheses, means it's a solid. G in the little parentheses means it's a gas. L in the little parentheses would be a liquid. And liquid, oftentimes you'll see if water is involved, they'll just put it like that. So it means water as a liquid compared to water as a gas. The last one you might see is you might see something that's listed AQ. So the term AQ stands for aqueous. Aqueous means it's dissolved in water. So you might have NaCl, AQ. So this might be a reaction where you have salt dissolved in water, but the salt is going to do a reaction with whatever substances are there. So sometimes water acts as like a medium. Everything needs to be in water so they can kind of float together and be able to interact. In the human body, that's the only way we could get reactions to occur. Because otherwise things would just be too far apart. But water allows this medium for things to float together. So in this one, we don't really have water involved. Carbon combines with oxygen, it makes carbon dioxide. So you see, they have carbon kind of as that little gray sphere. So they're saying if you have carbon as a single gray sphere, it combines with 2 oxygen atoms because O2, the formula of O2, means there's 2 oxygen atoms per molecule, per component. And see how you end up at the end. One little gray ball is still one little gray ball. 2 red ones are still 2 red, but now they're combined. So you see how you don't gain, you don't lose. They're exactly the same. So one carbon atom reacts with one oxygen atom and forms one molecule of carbon dioxide. So they're even amounts. But oftentimes when, like with this one, I took magnesium. Magnesium was the solid. That was the little metal strip. And I ignited it, just like you do with the charcoal briquette. So I lit a match and put the flame to it. And it's the oxygen in the air that reacts with it. And it made magnesium oxide. It made that little white ashy solid material that's left in the dish. While the reaction occurred, it gave off a really bright light. This was actually the premise behind, like in very early photography. If you've ever seen it, how they used to have the big camera, like the guy had like, it was a camera like this big, stood on a big tripod, and the guy would like put his head inside of the thing to be able to focus it. So the film for those were huge pieces of film, and he would hold this little, it was like a little pole, and he would actually light that. That was actually little pieces of magnesium that they would lay up on that pole, and when it would burn, it would create that bright light, and that would actually light the room up so that they could actually expose their film. So depending on how old you are, have you ever seen what they call a flash cube? Does anybody remember the little 110 film, and they had little flash cubes? Maybe your grandparents had them. So when you would go to take it, it'd be like it'd go, poof, and you get this super bright light, and everybody would be like, oh, that's great. And then you'd be like blinking and feel like you were blinded for a good 30 to 45 seconds afterwards. Same thing. Same exact thing is to generate that amount of light. So that was one of the sort of indications that a reaction was occurring. But in this one, what do you notice in terms of amounts? Magnesium starting, there's one magnesium per little metal piece. And then over on the product side, I have one magnesium in the formula. So you see that those are okay, those are the same. But what about oxygen? Yeah, so oxygen on this side, I have O2, which is like I have 2 oxygen atoms per molecule. On the product side, it looks like I only had 1. So it looks like I lost an oxygen somehow, okay? But the rules are with this is that you have to have an equal number of particles will react and form so that you can account for the atoms. And you do that by changing the coefficient. That is the number in front of the molecule. So that tells you how many molecules react together to form the product. So to do this one, so magnesium plus oxygen, I'm just going to rewrite it here. Mg plus O2 to MgO. And I'll leave the solids and the gas parts off just so that you don't get those ones mixed up, because they're just telling you what the state is. So the way that I do this is I always put a line through my arrow, because that helps me to remember everything on the left is reactant, everything on the right is the product. So line through the arrow. Second thing that I do is I list the number of atoms by the formula. So Mg, that means that I only have 1. So over here, 1 Mg. Over on the reactant side, how many oxygen? According to the formula, I have 2. And I write OXY for oxygen, because otherwise, if you write 2 capital O, it looks like 20. And then people get that mixed up because they're like, I have 20. I don't know what that is. So I always just put OXY so that I can remember it's not a 0, it's an O. Okay, so I have 2 oxygens That's the number of reactants. So you're going to list it on the reactant side and separately list it on the product side. So when I look on the product side, now I have MgO. So MgO means that I have 1 magnesium and 1 oxygen. Based on the formula, that's how you know which ones are there. To be able to balance the equation, I need to determine how many of each molecule I need so that I have equal numbers of magnesium, equal numbers of oxygen on both sides. So my magnesiums are already balanced. They're already 1 and 1. The one that's not balanced is the oxygens. So if I have 2 oxygens according to the formula on the reactant side and only 1 on the product side, that means how many magnesium oxides do I have to make in order to have 2 oxygens? How many of these, how many magnesium oxides, MgOs, would I need to have 2 oxygens? I have to have 2. So I'd have to have 2 of those, right? So 2 MgOs. That would give me 2 oxygens. So this 2, to check yourself, it would be 2 MgOs. So that means now that would give me 2 magnesiums and 2 oxygens. So that balances my oxygens. Unfortunately, what does it do to your magnesiums? On the reactant side, I have 1, and now on the product side I have 2. So I have to go back and fix that. So now I have to go to the magnesium on the reactant side. How many magnesium do I have to start with to make 2 magnesium oxide? 2. So that 2 means that I have 2 magnesium atoms. But that 2 does not change the oxygen on the reactant side. So since it's this number 2 is only going to affect what's right behind it. So it's 2 magnesium. Same thing with this. That 2 is for the whole molecule, both the magnesium and the oxygen of that molecule. So now when you look at it, 2 magnesiums total, 2 oxygens total. And so the one that's left empty, if it's empty, that means that it's already balanced. That means that it would just be a 1. So you're going to change what are called the coefficients. To balance each element type. Because the law of conservation of matter says you can't make or remove, you can't create nor destroy matter. So you have to be able to balance it. And the way that I would read this is I would say 2 magnesium plus 1 oxygen make 2 magnesium oxides. And if you don't know the name of an MgO, you could just say 2 MgO molecules. So that's a balanced equation. And I've got a whole 2 pages in that worksheet. So the worksheet that I gave you is the handout. The last page is just 2 pages of balancing equations. So some of these are in there. That handout that I gave you on the very first night, it has like the exam review on the first page, unit conversions is the second page. Well, this is the 3rd page. So here, magnesium plus nitrogen makes Mg3N2. So the steps that you do when you go to balance, first thing, draw a line. Okay? Because that's just going to help you to split. Remember, everything on the left and everything on the right. Everything on the left is reactants, everything on the right is product. Second thing to do, list the number of atoms based on the formula. So we have 1 magnesium, 2 nitrogen on the left side, just from the formula. So if it's just Mg, that's just 1. N2 means 2 nitrogen. So how many magnesiums on the product side? Yeah. So I have 3 magnesiums. How many nitrogens? 2. So it's just based on the formula. So the number after each element tells you how many in the molecule there are. So the next thing is to look and see, are there any that are balanced? Yes. Nitrogens are, okay? So if the nitrogens are balanced, then we don't have to worry with them. Let's balance the magnesiums. You're always going to change the one that's smaller, okay? And you're going to change it by figuring out how many of those molecules you need to make them equal. So on the product side, I have 3 magnesiums. On the reactant side, I only have 1. So how many magnesiums do I need to have in order to give it 3 on the product side? What do I have to put up here? 3. A 3. So if I start with 3 magnesiums, that 3 is only going to multiply the number of magnesium on the reactant side. It's not going to change the nitrogen because they're 2 separate reactants. So now, 3 magnesium, 3 magnesium, 2 nitrogen, 2 nitrogen. Is it balanced? Yeah. So anything that you didn't have would just be a 1. Okay? And I give people the analogy, like when you cook, you don't use a cup of sugar or a cup of flour, a cup of eggs, a cup of butter. You have different ratios of them. And that's kind of what you're doing, is you're figuring out what are the ratio of these molecules, how many of each molecule you need so that all the reactants, the total number of each element on each side is the same. And you do that just by changing the coefficient, the number in front. You're not going to change the formula. I'm not going to change that Mg3N2. That's like set in stone. So the name, the formula, you can't change the formula, but you just change the number of molecules of each to get it balanced. So what does it mean when you see this parentheses thing? What does it mean in math? So if I have Al2CO33, how many aluminum? Yeah, so I got 2 aluminum because that's Al2. And then CO33, what does that mean? 3 carbons and? Nope, 9, because remember it's times. It means this, everything inside is found 3 times. So it's like saying I have CO3, CO3, CO3. So everything inside gets multiplied times 3. So 3 carbons and 9 oxygen. That parentheses, and you'll see why we do it that way once we talk about polyatomic ions. But that 3 outside means everything inside is multiplied times 3. What about on the product side? Al2O3 is 2 aluminums, 3 oxygens. Pretty cut and dry. And then CO2. 1 carbon and 2 oxygens. So all you have to do is you just look at whatever number is after each element, and if it doesn't have a number, it's a 1. So CO2 means 1 carbon, 2 oxygens. Now notice here, I don't combine my oxygens because they're in 2 separate molecules on the same side. So list them separately, but I usually try to create like a little bracket connecting them to remind myself that a total number of oxygens on both sides have to be the same. So list, if you have the same element on one side, you are going to have to add them together when you count the total number. But when you balance it, you may balance one oxygen group and not the other, just because you may be changing one molecule, putting a coefficient in front of one, and you're not necessarily putting it in front of the other one. So don't list them together, okay? Just list them. So I just always go through and just list what's there in order. But then I'll put a little connector, so that tells me go back and add my oxygens at the end. The other rule I have is if you have something found more than once on one side, save it till last. Don't try and balance it first. Balance the simple ones, because most of the time when you balance the simple ones that are only found in one place on either side, it'll balance the more complicated ones. So looking at this, 2 aluminum, 2 aluminum. So my aluminum are balanced. 3 carbon, 1 carbon. They're only found in one place, so I can balance those next. So balance the carbon. What would I need to do? Which side am I going to change, the right or left? Product side. Okay, so if I only have 1 carbon in CO2, how many CO2s do I need to have? 3. Yeah, so 3. I put a 3 in front of the CO2. That means that I am going to multiply the carbon and its O2 pair as well. So both the carbon and the oxygen, because that 3 is in front of that molecule. Okay, when you do it, then go back and look. Did you mess up your aluminum? Because sometimes that happens. That's okay. If it ends up changing one that was balanced and now it's not, just go back and rebalance them. Aluminum and aluminum are balanced. Carbon and carbon are balanced. So what about oxygen? So on this side I have 9. On the other side I have 3 and 6. So that one's balanced. So like I said, a lot of times the ones that are more complicated, you'll see them balance themselves as you balance the simpler. So you want to balance elements found in only one balance elements found in only one place on each side first. Those are the ones I call the simple ones. So for me, aluminum here would be simple. Carbon, those are the simple ones because they're only found in one molecule on either side. Leave the more complicated ones till the very end. Sometimes you have to balance those, but a lot of times they'll fix themselves.
So would you just put 1 in front of?
Yep. 1 and 1. I didn't do anything to those, right? I didn't have to change those, so if you didn't, then that means it's a 1. So you would read this that 1 Al2CO3 reacts to form 1 Al2O3 and 3 CO2s. So that would be like if it was a chemical sentence. The arrow means reacts to form. You always like read the reactants, then the products. Okay? All right, so I want you to try a couple of these. Like I said, you've got these. These ones are all in that review page. I don't think I actually made any. All right, so what's the first thing you did on this first one? One is, right, put a line through the arrow, split it. Reactants on the left, products on the right. So how many do you have? 2 H. 1 oxygen, and 1 sodium. Good, so you're learning the elements too doing this. What about on the product side? 2 H, 1 sodium, and then 1 more hydrogen. So just connect them. List them separate, but then connect them so you know to go back and count them. Okay? So since hydrogen are found in 2 places on the product side, leave that. So check the other 2 first. So sodium, how many on each?
1.
Oxygen, how many on each?
1.
Rats. So that means that you actually have to balance the hydrogens this way. So on the reactant side, I have 2. So I know on the product side, I have to have some even number, right? In order for them to balance, they're going to end up having to be even, because that's always going to be a multiple of 2 with water. So how could I make the product side have an even, what's the smallest even number? What could I change? Change which one? Do I want to change the hydrogen or change the sodium, the NaOH?
NaOH.
What could you do?
Put a 2 in front of it.
If you put a 2 in front of NaOH, well, let me change my color. I don't like red. So if I put a 2 here, okay, you'll see that that's going to double that hydrogen, and that'll give me 4 over there, but it's still an even number. That's like the smallest even number I could make on the product side. So if I made this a 2, that's going to double this and this and this. It will double Na and the O and the H. So now I have so what happened in the balancing? You just messed everything up. When you go back and look at it, you're like, okay, now nothing's balanced. Okay, but I'm going to go back now and balance it, because what can you do then with your sodium? So if I put a 2 on the left, 2 times 2, so now I got 2 sodium and 2 sodium, so those are balanced. What can I do with the oxygen? So go back and balance the simple ones again. So oxygen, put a 2 in front of the water. Now that is going to multiply my hydrogen by 2 and my oxygen by 2. Now I've got 4 hydrogen, 2 oxygen. So now look back. How many hydrogen total? 4 and 4. How many oxygen total? 2 and 2. And then sodium total. 2 and 2. Okay? So in that one, what would this one be? Just a 1. So it doesn't always necessarily have to have a number. If you get done, everything's balanced, that means that you would just have 1 hydrogen as part of that product. So this looks like a lot. Just make sure that you multiply everything times the inside when you have those parentheses. So this is 2Al, 3 S's, 12 oxygens, 2 hydrogens, 1 oxygen. And so these two, connect them, because those oxygens are together. Then over on the other side, 1Al, 3O, XY, 3 H's, 2 more H's, 1 sulfur, and 4 oxygens. So that one, you have oxygens paired and hydrogens paired on the product side. So it looks a little busy, but again, balance the simplest. Which ones are the simpler? Which one would you do? Aluminum. Okay, so aluminum on the reactant side, you have 2. Product side, we have 1. So we know we're going to change the lower. So how many of those do you need to have 2? 2. Okay, so that 2 multiplies AlOH3. So it's going to multiply the Al, the O, and the H of that molecule. All is going to get doubled. Okay, so what's the other one that's found simple?
Yes.
The sulfur. Okay, so on the product side, I have 1. Reactant side, I have 3. So I'm going to have to change. How many H2SO4s do I need? On the product side, how many H2SO4s to have 3 sulfurs? 3. So each H2SO4 has 1 sulfur, so I need 3 of them. So you put a 3 in front. That 3, I have to multiply all of the components of that molecule by 3. And you're like, geez. Now you have a holy mess. 2 aluminum though. 3 sulfur, 3 sulfur. So now look at hydrogen, because hydrogen is only in one place on the reactant side. So that's kind of like the next simple. So look at hydrogen, 2 hydrogen on the reactant side. How many hydrogen total on the product side? 12. See these 2? I have 12 hydrogen. So if I want to have 12 hydrogen on the reactant side, how many water molecules? How many H2O? So I'm going to have to change that. So this is going to need to be a 6. That means that this is a 6 and this is a 6. So then now I have 12 hydrogens. And 6 more oxygen. Go back and double check. I still have 2 aluminum, 2 aluminum. Still have 3 sulfur, 3 sulfur. Now I have 12 hydrogens and 12 hydrogens, yes?
Yeah.
All right, so now check oxygen. How many total on the reactant side?
18.
18. How many on the product side?
18.
18. So a lot of, that's what I said, the more complicated ones, they kind of like just did themselves. So this would be a 1. Okay, so tell me what's in the list. On the reactant side, there's 2 Cls, 2 H's, 1 oxygen. Good. And then on the product side,
1 hydrogen, 2 oxygen.
yep. So notice we're all 1 and 1 and 1. Okay, so they're all just in single places. So just pick one. Okay, so you can just pick one to start with. None of them are balanced.
I did oxygen.
You started with hydrogen? You
I did
started,
oxygen.
and you did oxygen. And I mean, you can pick whichever one you want, okay? So for me, oftentimes I just start with whichever one's first. But whichever. So if you started with hydrogen, we'll start there. So 2 hydrogen on the reactant side, only 1 on the product side. So in order to make it 2, how many do I have to put in front of HCl? 2. So I have to have 2 HCl's, but now remember that's going to double the hydrogen and the chlorine. So I try to do it with colors because I think it's a little easier to see and follow. 2 H's and 2 Cl's. Go back. Okay, so what did that do? So my hydrogens are good. Now my chlorines. Hooray, the chlorines are balanced. So chlorines, by balancing my hydrogens, I balance my chlorines. So now all I got to do is balance my oxygens. So to balance the oxygen, which side do I have to change?
Reactant.
The left side, the reactant side, because it's lower. I only have 1 oxygen on the left. I have 2 on the right. So how can I make the oxygen number on the left 2?
You have to do 8 times 2.
So I have to put a 2 in front of the H2O. That means times 2 times 2. So now 4 H's, 2 oxygens. And what did I do?
Unbalance the hydrogen.
I unbalanced the hydrogens. So my chlorines are balanced, but my oxygens are not. My chlorines are balanced, but my hydrogens are not. So now I got to go back and I've got to balance those. So I'm going to have to change that HCl number. So I had it as 2. So how many does it need to be?
4.
So you can think of it, you can either erase and redo, or you can just say, well, I'm going to have to multiply it times 2 more, right? So times 2 more, times 2. It's both the H and the Cl. So that will give me 4 hydrogens. That will give me 4 chlorines. So I fixed my hydrogens, my oxygens are good. So the only thing I have to do is fix the chlorines now, right?
Yes.
Okay, so which side do I have to change?
Reactant.
The reactant side on the left. So on the left I have 2 chlorines, and on the right I have a total of 4. So I'm going to change the left. How many would I need to change it to? I'd have to have 2 chlorines times 2 gives me 2 chlorines.
4.
Oh, sorry, 4 chlorines. That's a good thing because that means I am balanced. So 4 chlorines on both sides, 4 hydrogens on both sides, 2 oxygens on both sides. So this, you would just change this to a 4, 2 times 2. Okay? And I'll just go back and change it at the end, just because that way if I had to go back and multiply it again, sometimes I've had to do that, go back and forth. So that means that oxygen is it's just a 1. I didn't have to do anything. So 2 chlorines plus 2 waters reacts to form 4 HCl's and 1 O2. So that's the balanced ratio, and that's all that you have to do. And the ones that I've given you, so on that worksheet, There's a page front and back of nothing but balancing equations. There's only like 2 that are kind of complicated. Like on all of those, it's just a good practice. The answer key is posted in lab. The answer key is also posted in Moodle. So they're posted as pictures. So if you click on that link, it'll just show you it's just like a JPEG picture. So it'll just open an image picture of that balanced equation so that you can practice these. We will do, like I've got another one. So we'll do these. These ones are a little more interesting. So we'll do these next time just to kind of like back up and then practice again and then move forward from there. That finishes chapter 1. And chapter 1 is really thick. Chapter 2, we can cover in a lecture and a half. Like it's that short of a lecture. It's really not bad at all. So chapter 2 is sort of like application of some of this element, compound, information, periodic table. So in chapter 2, it's all about like atoms, what you can tell about atoms and how it relates to radioactive substances. So in doing studies on the atom, they came up with these subatomic particles. So subatomic just means these are the particles that make up the atom. And there's actually smaller groups of subatomic particles like leptons that we're not talking about because we don't really need them for what we're going to be using them for. So if you just think of the atom as like a sphere, just think of it as sort of a ball. You have a very, very small center. And so, much like a cell, they called that very, very small center the nucleus. And in the nucleus, they found 2 subatomic particles. There are protons and there are neutrons. Protons and neutrons are almost identical because they have the same mass. But protons and neutrons differ because protons have a positive charge. So oftentimes you'll see them drawn as a P with a little plus. Neutrons are neutral. So you'll see them written as an N with like a little 0 sign, like no charge. The third thing they found is they found electrons. Electrons are not in the nucleus. They're outside. Outside the nucleus is where they found electrons. Electrons have a negative charge. So you'll oftentimes see them written with a little e with a negative sign. So when they started trying to talk about actual mass of a single proton, neutron, and electron, super, 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 super small. Remember those like the 1.6 times 10 to the minus 19 grams? When you're talking about like exponents that are super, super small, because these are submicroscopic. Even now with our strongest electron microscopes, we can only see the shadow of atoms. So like if you take like lead and pound it super, super thin, you run electron microscopes over it, you can see the shadows of it because lead's really big. And it's just because those are really big atoms. So these are super small, tiny particles. So they were like talking about something in mass of like 1 times 10 to the minus 19 grams. Keeping that exponent, that's sort of a pain. So they said, well, how big are they comparatively? How big are protons and neutrons and electrons relative to each other? So they said, well, protons and neutrons they have about the same mass. So their mass is about the same. But when they started measuring the mass of electrons, they were about 2,000 times smaller. So they said, well, if it's 2,000 times smaller, electrons are not really adding anything to the mass. That the mass of your atom is, for the most part, protons and neutrons. So they said, well, we can give them relative mass, so we don't have to talk about all those negative exponent values. We can use what is known as an atomic mass unit, or AMU. Atomic mass unit is just a relative mass, and these protons would have 1 AMU, neutrons have 1 AMU. So we'll say protons and neutrons each have a mass of 1, and it's not like a gram. They don't even give it a unit. They just say relatively it's got a mass of about 1. But electrons are 2,000 times smaller, so relatively electrons have a mass of 0. They don't actually not have mass because then they wouldn't be matter. They do have mass, but it's so small it's negligible. It makes no difference. So they have 0 AMU. So that just shows you like differences between protons, neutrons, and electrons. Protons and neutrons in the nucleus. Protons and neutrons have mass. Protons are positively charged and neutrons are neutral. So that's a way that they differ. Electrons are really like different because electrons are outside the nucleus, electrons have a negative charge, and electrons have almost no mass. When they started looking at the periodic table, they were like, well, do elements seem to go according to, do they follow numbers of protons, numbers of neutrons, or numbers of electrons more? And they found that characteristics of atoms are really based on their numbers of protons. So that number at the top on the periodic table above each symbol, they called the atomic number. And the atomic number, I could jump forward. Where are we? Here. The atomic number defines an element. All atoms of the same element have the same atomic number, and that's the number of protons. So on the periodic table, in a block, so we have carbon, number above, 6. The number below, 12.011. That 6 is the atomic number. That tells you the number of protons. Every atom that is carbon has 6 protons. So that defines what the element is. So if I said, what is the element that has 8 protons? You would look at the periodic table and you would say, oxygen. So you could define, you can define it by numbers of protons, you could define it by atomic number, you could define it by symbol. And I would only ask you the 30 that you had to know anyways, but that is how, all you have to do is look at the periodic table. So remember the number above. And so in your laminated sheet, it's the number that's like always directly above. This one, they put it like in that upper right corner in the block. It's just a weird periodic table, but it's always above. Okay, on the periodic table, the number above, it's always a whole number, it's always the atomic number, and it always tells you the number of protons. However, in an atom, atoms are neutral. So if we have 6 protons of carbon, what else do we have 6 of? Not neutrons, because those are neutrons. If we have 6 positive protons, then we're going to have 6 negative electrons. So the atomic number also tells you the total number of electrons. So you don't even have to figure it out. All you got to do is look at the periodic table. So if I'm like element number 11, what is it? You look at the periodic table and you go, oh, that's sodium. And how many protons does it have? 11. And how many electrons does it have? 11. Okay, so you can tell that just from looking at the periodic table. No need to memorize it or anything. So you've already got that. So the only thing that's left are the numbers of neutrons. And that comes from this. Okay, so the bottom number in each block, notice that it's this decimal. Okay, the bottom number, this is the average atomic mass. So what were the 2 particles that I said have mass? And neutrons. So this is protons and neutrons. So if you take the atomic mass and just round it to the nearest whole number, subtract atomic number, that is taking numbers of protons and neutrons, taking away numbers of protons, and that'll tell you numbers of neutrons. So if you take the atomic mass, that's the bottom number, just round it to a whole number. Subtract the atomic number, the top number. Atomic mass is the number of protons and neutrons. Taking away the atomic number takes away the protons, and that'll tell you numbers of neutrons. Okay, so the bottom number rounded, or the bigger number, you could even remember, take the bigger number minus the smaller number. Just round it, round that crazy long decimal place number, just round. Bigger number minus the smaller number rounded to the whole number is numbers of neutrons. So let's do some. Ag, what is Ag? It's one of your elements, silver. Somebody's been working on them. Okay, Ag is silver. Find it on the periodic table. Tell me how many protons? 47. What else is 47? Electrons. Right? Atomic number tells you number of protons, and in a neutral atom, it also tells you number of electrons. Numbers of neutrons. So here we got, if you look at your periodic table on your 107.9, so round that to 108, just round up. 108 minus 47 is 61. That's numbers of neutrons. Don't have to memorize it, just have to use a periodic table. And you always get a periodic table. That's why I'm like trying to give you all, there's lots of information that can let you figure out. You don't have to remember those things, you just have to know what the numbers are telling you. So I said Na is sodium. Number of protons? 11. Electrons? 11. Neutrons? 12. Take 22.99, round it to 23. Subtract the top number, subtract 11, tells you 12. And you will see with the little elements, protons, neutrons, and electrons are typically really close. Like they might be different by 1 or 2, but they're not oftentimes different by a lot. But when you get to the big ones, TH, where is TH? That is not one you have to know, so that is one I would tell you. Nope. Thorium. Like the Greek god. Thor. They don't name them after people unless they're dead. Like, so there's some elements like curium named after Marie Curie, but that was after she died. So you don't get elements named until you're dead. But there's like californium, berkelium, there's europium. So they're kind of interesting ones, but thorium, Thor, is what I always think of. So how many protons does he have? 90. It's humongous. How many electrons then? 90. Now, figure out neutron number. Yeah, 232 is its atomic mass. It's big. And it's got, take away the 90, it's got 142. Not surprising, it's not very stable. Really big numbers of neutrons, more neutrons than protons and electrons, not as stable. That's where you get the radioisotopes, okay? Krypton, which really does exist, much to Superman's sadness. Where is it?
36.
So that's how many protons?
36.
How many electrons?
36.
How many neutrons?
84.
Minus?
36 is 48.
48. It's an 8. It doesn't look like an 8, sorry. There. HG, you know that one. HG, MMHG. Mercury, good. That's in your list. Find it. 80. 80 protons. How many electrons? 80. Now neutrons.
120.
So you would take 201, because it's 200.6, so we'd round up, so it'd be 201 minus 80.
121.
121. It's actually pretty stable to be as big as it is. Maybe it's because it's a liquid. I don't know. And then Zn is zinc. That is one of your list. Find it. Protons. 30. Electrons. 30. They're always the same. Protons and electrons in a neutral atom always the same because positives and negatives balance. So then to get the neutrons.
65 minus 30.
Yep. So really not too bad. Okay. So we'll quit there. We're going to talk about some of these really big elements and what happens if their nucleus has too many neutrons in them, why they're unstable, how they're radioactive, and how you may come across this in the medical field. So we'll talk about like x-rays, and we'll talk about like radiation therapy, the different forms of that and ways we can use it diagnostically and therapeutically. So we do not have class Monday because it is Labor Day. I always say Memorial Day, but it's Labor Day. That's why I thought I'd let you finish that because I was like, God, we say the wrong one. I can never remember which one's which. But so we won't have lecture again until Wednesday. We only have one more lecture before the exam. Just saying. So go ahead and finish chapter 1. Okay, go ahead and start looking at chapter 2, going through information, continue practicing your unit conversion, significant figures. Really make sure you get this part down, and you can start working on the proton, neutron, electron numbers, recognizing those off the periodic table. Okay? What? Exam what?